Thank you all of you for being here, and I'm very grateful for the invitation. So this is work with Charlie and Sanjoy Mitter on fitting manifolds to data. So Charlie spoke about this question when in his first talk, and he mentioned that I'm going to put a slightly different spin on it. It's not so much a different spin, but there's a kind of pre-processing step which is something that's natural from a statistical point of view. You're looking at a probability distribution rather than a set of points. But the hard part of it is exactly the questions that people have been discussing in this meeting here. Because once you get the data, then what's it that you do with it? So I'll start with some general spiel. So we know that nowadays one is interested in analyzing very high-dimensional data. This includes data from spectral medical imaging, but this is hyperspectral in that there are many different frequencies over which these things are taken, not just RGB. So they're very high-dimensional, and also gene expression data. One characteristic of a lot of the data that is analyzed today is that the number of dimensions is either comparable or even larger than the number of samples. And this takes us into a domain that is different from classical statistics, where you're in a fixed number of dimensions and you get more and more data samples, and you start looking at various kinds of central limit theorems or convergence results. But here, you never have that much data compared to the dimension. And so you're in a regime where both the dimension and the number of samples either scale simultaneously, or even a situation where the number of data samples is small compared to the number of dimensions. And this sort of, the analysis of this kind of data is associated with what is called the curse of dimensionality, which is basically that if one is not very careful in defining the kind of function classes one studies in high dimensions, the sample complexity of the task grows exponentially as the dimension increases. So for example, if you wanted to specify one Lipschitz function in a unit cube in Rn, up to epsilon everywhere, you would require at least 1 over epsilon to the n samples. And if n is large, this is not feasible. So you have to be very careful in the kind of functions you're looking at. So there are some characteristics of such data analysis that are also positive. They are called blessings of dimensionality. At least such a term was used by David Donohoe. And one of these is concentration of measure, which is the phenomenon that many random quantities in high dimensions start behaving like deterministic quantities. So for example, if you take any arbitrary probability distribution in the unit ball in a high dimensional space, a Euclidean ball, and you take a random line and you orthogonally project a random sample from this distribution onto the line, the random variable that you get on that line will converge in distribution to a point mass. At least the variance will be of order 1 over n, where n is the dimension. And so this is something that in some sense becomes an easier question when the dimension increases. And also asymptotic analysis becomes easy in high dimensions quite often. So these are all things that in some sense allow you to get around the curse of dimensionality. They don't really improve matters, but in some sense matters don't become worse. So there are several ways in which data analysts try to deal with the curse of dimensionality. All of them are in some way or the other related to studying very special classes of functions that in some way counteract the difficulties associated with increasing dimension. One that is traditional in statistics is to try to look at functions with more and more derivatives in higher dimensions. And so then in some sense the richness of these function classes do not grow as the dimension increases, because it's counteracted by an increase in regularity. And another thing that has nowadays been studied a lot is to say that although data is very high dimensional, it's actually sparse. So there are actually only few coordinates that are non-zero and matter. And so the effective dimensionality in many ways is not the length of the vector, but something like the sparsity multiplied with the logarithm of the dimension. A third method that has also been studied is the basis of manifold learning. Here, the assumption is that although data is high dimensional, it actually is supported in the vicinity of a low-dimensional submanifold. And the reason is that the generative process possesses some symmetries or a low number of degrees of freedom, intrinsic degrees of freedom, and this gets reflected in the geometry of the data. And though it is high dimensional, it somehow lies in the vicinity of some low dimensional manifold. So that's going to be the subject of today's talk. The manifold hypothesis is that the data lies near such a manifold, and manifold learning is a way of doing data analysis assuming that the manifold hypothesis is true. But it is contingent on the manifold hypothesis being true. That's at least the rationale that's given for many of the algorithms. So this begs the question, when is the manifold hypothesis true? Now it's true that this is not only a question about the data, it's a question about the representation of the data. So for example, if I took a camera and moved it around here, then if I parameterize the images by the position and orientation of the camera, that would be something that would be smooth and on a manifold. But the images themselves, if one measures them in L2, they might not really be a smooth manifold, because the images change very rapidly under a small shift. So representation is important, but that is something I'm not going to discuss here. I'm only going to talk about whether a particular representation of the data lies near a manifold or not, and study the statistical and algorithmic aspects of this question. So in order to ask whether or not data lies near a submanifold, I have to say what I mean by submanifold. So this is what we'll mean. We're going to be parameterizing the complexity of a submanifold by the reach, the volume, and the dimension. So the reach of a submanifold is the largest number tau, with the property that for any r less than tau, any point at a distance of r from M has a unique nearest point on M. So there's a unique projection. I'm also going to assume that these manifolds are CR manifolds for some r greater or equal to 2, but I'll not, that's going to be a standing assumption. So here, for example, is a curve with large reach, and here's a curve for small reach. Reach is something that has both global and local implications. So a bound on the reach implies a bound on the curvature of the manifold, but additionally it implies something about non-intersection. So for example, if you have two parallel lines that are at a distance of 2 tau from each other, although these lines are straight and have no curvature themselves, the reach of the union of these two is tau, because there is a point that is equidistant from these two lines at a distance tau from each, and it does not have a unique nearest point on the set. So we'll consider the following class of manifolds. These are the manifolds which are dimension D, volume V, reach tau. As I said, they are CR submanifolds for some r greater or equal to 2, and so the volume is at most V and the reach is at least tau. And we are going to be interested in asking whether the data lies near a submanifold in this class of submanifolds. So this question has a statistical aspect and an algorithmic aspect. So in order to talk about this, the statistical aspect is the following. This is how we model the statistical question. It's this framework of computational learning theory that was pioneered by Wapnick, where it's about learning in the presence of uncertain data. So here's the model. We assume P is an unknown probability distribution supported in the unit ball in a separable Hilbert space, and that there is this continuous stream of x1, x2, etc. of IID random samples from P. So given an error tolerance epsilon, the dimension D, volume V, reach tau, and a confidence 1 minus delta, we are expected to produce an algorithm that takes a number of samples that depends on these parameters and outputs whether or not there is a manifold in the class of interest, such that with probability at least 1 minus delta, the expected squared distance of a random point chosen from this unknown probability distribution P to M is less than epsilon. So note two things. First, that we are going to have to infer something about P just from the IID samples x1, x2, etc. And secondly, the number of samples cannot depend on the dimension of this Hilbert space, because this could be infinite. So although we are working in an ambient dimension that is potentially infinite, what we want to say is that you can choose a number of samples that depends only on the dimensions of these manifolds that we are looking at, and from that we can tell with some probability whether or not this P is somehow concentrated near a manifold of interest. So there are two aspects to this. First, what is the number of samples you need before testing the hypothesis that data lie near a low-dimensional manifold? In other words, how many samples do I need before which there exists some process that will take those samples and then output a correct answer of whether or not there is a manifold? And the answer to that is that it depends only on the intrinsic dimension, volume, and reach, but not the ambient dimension. And incidentally, I forgot to mention, we actually also can give some sort of description of a nearly optimal manifold. It's not just a yes or no thing. We also have a description, but these things are not exactly optimal. They're optimal up to a controlled constant C, of the kind that we have seen in Charlie's lectures. So first there was that statistical question, and then there is the algorithmic question that is more challenging, and which is that if you given x1 to xn in the unit ball in the separable Hilbert space, is there a manifold in the class of interest? Here C is a controlled constant, such that the average of the distances to this manifold is less or equal to C times epsilon. And here is C is some constant depending only on the intrinsic dimension of the manifold. So this is where techniques from interpolation will come into the picture. So so for better or worse, I'm going to spend a fair amount of time on the sample complexity. But perhaps since you have seen a lot of interpolation here, it won't be entirely an unwelcome change. Okay, so here so LMP is So let LMP be the expected squared distance of a random point to M, and let the empirical loss be be defined as the average of the sum of the squared distances. What we can measure from the data is this. What we are actually interested in is this. And the sample complexity is defined to be the smallest s, such that there exists some rule A, such that given x1 to xs, that rule will produce a manifold MA whose loss is good compared to the best possible loss of a manifold in P. Here we do not even ask for this rule to be computable. It has to just be some rule. So sample complexity is not about computability at all. It's just about informational complexity. And of course, if any rule is good enough, then the following simple rule would suffice to give an upper bound on the sample complexity. Pick those samples, fit the best possible manifold to those samples. So that's the process of empirical risk minimization. And if what you're interested is in minimizing the blue curve, which is the actual loss, and what you observe from the data is this red curve. So here is the space of manifolds, and here is the loss. If you want to be able to optimize the blue, and if you can prove that the red curve is uniformly close to the blue, it's good enough to optimize the red, because then that's going to be very close to the blue, the minimum of the blue. So that's the approach we're going to take. And it means that we're going to try to prove that uniformly over the space of all of these manifolds, the true loss measured using the probability measure is close to the average loss measured using the empirical sample x1 to xs with high probability. So here, this is the kind of uniform bound that we're interested in. We want to say the probability that the supremum over all manifolds of interest of the average squared distance to a manifold to the true squared distance of the manifold being less than epsilon is greater than 1 minus delta. And the question is how large must S be, or how much data do you need before this is true? And so the first theorem is that that this number is bounded above by v times 1 by epsilon plus 1 by tau to the d plus log 1 by delta by epsilon squared. and that if you have this much data, then the probability that the empirical squared distance is close to the true squared distance is by epsilon is more than 1 minus delta. And I'm sorry?
What is tau?
Tau is the reach. Tau is the reach. Yeah. Yeah, so actually Charlie observed that this can be, epsilon is actually square root of tau epsilon, so it's true for square root of tau epsilon too. The basic idea is that you approximate these manifolds as point clouds, and you say that you can approximate the space of every manifold in the class of interest by a point cloud containing not too many points. And the reason you have not too many points is that these manifolds are nice. They have bounds on their reach and volume. So this is, you basically reduce the question to k-means, or a clustering question, by saying that you wanted this uniform bound, but instead of this uniform bound, which involves functions of this kind, distance of m to xi, each m can be viewed as a collection of not too many points, and you can you take a uniform bound over the set of point clouds. Every manifold can be approximated in Hausdorff distance to a point cloud. Not every point cloud can be approximated in Hausdorff distance by a manifold, but that is fine, because this is a larger class in some sense. So you prove a stronger uniform bound, it would imply a weaker bound. So the uniform bound on k-means reduces to a uniform bound over functions of the kind minimum 1 less or equal to I less or equal to k ai dot x, using some linear algebra, because of the notion, because the squared distance in a Hilbert space ends up being related to inner products. And the way to get a good bound over such classes of functions. So the key point here is that these are functions that are the minimum of k linear functions, but the problem is that these functions are defined on a ball on a separable Hilbert space. So the dimension is extremely high, but there is some other sense in which the complexity of these functions is small, namely that they are the minimum of k points and that they are Lipschitz. Also these functions are Lipschitz, that's very important. So somehow we want to get a bound that exploits the Lipschitz nature of these functions and the fact that they have a small description length of this kind. And this is a well-developed subject in empirical. It's called empirical processes, theory of empirical processes. There are many tools. So one tool that is used is called the Fat-shattering dimension. This is a class. So given a class of real-valued functions, the Fat-shattering dimension at a scale epsilon is the largest S, such that there exists x1 to xs and thresholds t1 to ts, such that for every -1, 1 vector of length s, b1 to bs, there is a function fb in f, such that for all I, fb of xi minus ti multiplied by bi is greater or equal to epsilon. So what this means is that if there exists some s points and some associated s thresholds, such that for every choice of up, down, up, down, etc., there is some function in the class that actually goes up, down with respect to the thresholds, but also it misses the thresholds by at least epsilon in each case. And so if you get an upper bound on this S, then you get an upper bound on the sample complexity. So that is what the procedure is. And so if you can get an upper bound, then through results of Dudley, so this is reminiscent of Dudley's entropy integral, except that in Dudley's entropy integral you get certain L2 covering numbers here. And there's a result of Rudolfson and Bershinen, which says that you can reduce those L2 covering, you can replace those L2 covering numbers with the Fat-shattering dimension. And this is removing certain log factors was a very technical, difficult result. But anyway, so this is the result. If you have a bound in the Fat-shattering dimension, then you get a uniform bound of the kind that you're interested in. And the VC dimension is a class of functions of 0, 1 functions. It's a measure of the complexity of a class of 0, 1 functions, and it's the largest n such that there are n data for which all 2 to the n partitions are induced by class boundaries of functions in F. So if F consists of indicators of half spaces, then the VC dimension is d plus 1. This is known. If you have a bound in the VC dimension in S, then by something called the Sauer-Schiller lemma, you get a bound on the number of ways of breaking up the set into parts, the number of possible partitions induced on a given set by the function class, even if S is larger than the VC dimension. So for example, if S is large, VC dimension of F, which is a constant, multiplied by log of S, is an upper bound on the logarithm of the maximum number of partitions of S that can be induced. So if you get a bound on the VC dimension, then you know that there are not too many ways of breaking up the data using the boundaries of the functions from F. So how much time do I have? I'm sorry. Okay, thank you. Yeah. So like I said, you know, there were two characteristics of the classes of functions that we wanted to exploit. One, that they were Lipschitz, and two, that they were the minimum of k linear functions. And a way that sort of preserves both of these structural aspects is random projection. So suppose you had some S points that shatter that shatter the collection at epsilon. What that means is that you have these S points, and for every binary vector B, there is some function in the class of interest, namely the minimum of k linear functions, that goes both up and down as governed by the binary vector. So if this is true, then it turns out that if I take a random projection of this thing, which is in a separable Hilbert space, so you take a random projection onto dimension log of S by epsilon square. Now, when you take the random projection, what you have to do is you have to take the linear span of these S points and take a random projection of that linear span, because it doesn't make sense to talk about a random projection from a separable Hilbert space in general, at least not in some sort of rotationally invariant way. So you do this in a finite dimensional setting, and now you observe that if the previous thing got shattered by the functions, they also get shattered due to the Johnson-Linden-Strauss lemma in the low dimensional subspace. But that low dimensional subspace is log S over epsilon square, and when you have log S over epsilon square, you can start using VC dimension and Sauer-Schiller lemma to bound how many partitions are there. So that is the idea, and you use VC dimension Sauer-Schiller lemma on the low dimensional subspace. So this whole procedure can be used as a sort of implementation of the probabilistic method, except that we're using the random projection to prove the existence of the sets of the kind we're interested in. Not exactly the existence of sets, rather prove the non-existence of sets, the kind we're interested in. Yeah. So the random projection gives a bound on the VC dimension, and then this gives a bound on the Fat-shattering dimension of k by epsilon squared log square k by epsilon. And this then gives a bound on the sample complexity, which has the form k by epsilon square log to the 4k by epsilon. So we reduce the question of uniform bounds over manifolds to uniform bounds over point clouds, and that corresponds to k-means, which is a question that has been studied independently in the machine learning literature. And there are known lower bounds of k by epsilon square. So the bound we have is k by epsilon square log to the 4k by epsilon, which is not very far from k by epsilon square, but it will be very interesting to get rid of these 4 logs by some methods. As a corollary, so this was a purely this was a purely statistical result. However, it has an algorithmic implication, and the implication is that if you take S that is sufficiently large, then in order to test whether there is a manifold such that the expected square distance is equal to epsilon, you can take an IID subsample of P and test if this IID subsample is close to some manifold contained in the affine span of these points. So if I remove the fact that I've written affine span here, it's just a restatement of the uniform bound. But the reason you can have put an affine span is that, let's say you have these S points, and let's say I've tried to fit the best possible manifold, and it ends up that it is actually somewhere out there in the separable Hilbert space. But these manifolds have a simple structure in the sense that if you take an epsilon net of these manifolds, where epsilon is small compared to the reach, and if you take the affine span of that epsilon net and orthogonally project the manifold onto the affine span, not only do you get a new set that is close in Hausdorff distance, you get a new set that is close in reach. So you don't affect the reach by much. So you can essentially assume that these manifolds lie inside a dimension that is something like this. You don't have to assume that these are manifolds inside a full Hilbert space. And then, if these manifolds are anyway contained inside a subspace, then you may as well rotate that subspace maintaining the points and assume that the manifold is in some affine span, not exactly of the points, but a somewhat larger space. You need a few more extra dimensions to give these manifolds breathing room, but that is not too much. Okay, so now we've come to the algorithmic question. The algorithmic question is that given n points x1 to xn in the unit ball in Rn, is there a manifold M such that M belongs to GE of D CV C inverse tau, such that 1 over n summation I equal to 1 to n d of xi to m the whole squared less or equal to C epsilon. So this is purely, this is exactly of the kind that we have seen in this conference. This is the kind of question. There's no probability distribution involved. There's a set of points, and we're asking if there's a manifold with certain constraints on the dimension, volume, and reach, such that the sum of the squared distance is less than epsilon. So here's a result. It says that there is a controlled constant C depending only on D, and an algorithm that takes some fairly large number of operations on real numbers, but these number of operations do not depend upon capital N. But note that it is probabilistic, so there's a log 1 by delta. And then with probability 1 minus delta, the algorithm outputs yes if there exists a manifold such that summation I equal to 1 to n of distance of x to m the whole square is less than epsilon, and no if there is no manifold. And in fact, in the yes case, it would also produce a certificate manifold that has close to the desired properties. And the reason why n does not figure here, rather we have a delta, is that we are subsampling. So we have these n points we are interested in, but now imagine there is a probability measure that is the uniform measure on x1 to xn. And then we can use our previous result that says that you can actually just choose IID, a small number of these, and then solve the question on this small number of random samples. You don't have to solve it on all of n. And all of this is possible because we were looking for additive errors here, and not not the kind of stringent bounds that were looked for in, say, Charlie's talk or the work of Charlie and Boas and others. So that's why you can throw away data. In those questions, you cannot throw away any data. So the outline of the algorithm is this. So any manifold is firstly contained inside an epsilon neighborhood of an affine subspace of dimension np of epsilon. So this is just a repeat of what I said of taking the affine span of an epsilon net. And so you can allow us to reduce the ambient dimension n to roughly np. And secondly, we reduce this question to testing whether a discrete evenly spread set of points lie on a manifold. So the reason for doing this is that if you're searching in the space of manifolds, this is a space that has it's combinatorially complex in the sense that even if you just were to look at the descriptions of simplicial complexes that were homeomorphic to these, there are an exponentially many types. So there's going to be some form of exhaustive search. So we have a form of exhaustive search wherein we try to nail down these manifolds up to a scale, up to distance of tau, roughly. So and that is done in an exhaustive manner. We don't know how to do that in a more intelligent manner at this point. But once you nail them down to tau, then you start looking at a tubular neighborhood of this guess manifold. So this is a set of evenly spread points that look like a manifold. We're taking a tubular neighborhood, and now we are restricting our attention to finding a manifold that is entirely inside this tubular neighborhood. And for doing that, this has the following steps. You first define a smooth vector bundle with the base space that is a tubular neighborhood of the data, and each fiber looks like a normal to the manifold. So if the manifold is d-dimensional, this normal is n minus d-dimensional. For every point in this base, you have a n minus d-dimensional fiber. So this is the first vector bundle. The second vector bundle is got as follows. So now you define a putative manifold, which is a kind of guess manifold, as the set of zeros of a specific section of the vector bundle. And that specific section roughly corresponds to the gradient of the squared distance to the manifold. So you take a function that looks like the squared distance to the manifold, you look at the gradient at any point, you project that gradient onto the corresponding fiber. That gives you a section of this vector bundle. You look at the zeros of that section, and that gives you a putative manifold. So that's the set of zeros of a specific section of this vector bundle. And then you get a new vector bundle, a new vector bundle where the base space is the putative manifold, and the fibers are the same fibers that we inherited from the previous vector bundle. So you have a new thing, and it turns out that so one can show that these fibers they're almost parallel, and any point in this tubular neighborhood is a member of exactly one fiber. So the manifold, in particular, of a manifold were to be contained inside this tubular neighborhood, it is a section of this vector bundle. So now we've reduced the question of fitting manifolds to a question of fitting sections of a vector bundle, and that is much more in the spirit of the talks of this conference, where we are actually interpolating over something like functions. So here they are like functions, except that the base is a manifold and the codimension corresponds to the fibers. And now we use technology developed here. So what you do is you're essentially going to locally fit sections. So we find these local sections by optimizing the squared loss over a space of second order jets satisfying Whitney's inequality. So actually we end up using some inequalities of Charlie's which have fewer number of inequalities. Going from quadratic in Whitney's case, these are linear, related to the well separated pairs decomposition. But anyway, so there's a convex set. Locally, there is a convex set of feasible jets that would correspond to a small C2 norm, and you optimize over this convex set the squared distance, which is a convex function, and you can optimize a convex function on a convex set. It is not as efficient. It's not the linear time algorithms that were discussed in this conference, but because we are looking at squared distance function, and there the loss function was some sort of L infinity loss. But you can do this in polynomial time, and not too bad, n to the 4.5 or n to the 5 due to something called Vaidya's algorithm of convex optimization. And so once you have these local sections, you patch them up using a partition of unity that is supported on the putative manifold. So you have these things, and you have this fiber, and then you have a partition of unity on the putative manifold, and use that to get a global section. And this is how we get the whole manifold. And so I should mention one key lemma that allows all of this to be possible is the following. It's something that you start with a function that's like the squared distance to a d-dimensional subspace, but using that, one gets a manifold, and one gets a disk bundle or a vector bundle of the kind that we're interested in. So you start with this function, which has the following properties. Its first alpha derivatives, first k derivatives are bounded, and you have this condition on f of x comma y. Here x is d-dimensional and y is n minus d-dimensional. So f of x comma y is greater or equal to the norm of y squared plus rho squared times some constant, and it is less or equal to norm of y squared plus rho squared with some constant. This rho is what allows us to model curvature. So if this were 0, then the 0 set of this function would just be affine subspace, but it's not 0, so you can start allowing for some curvature. So you have this function, and then what you do is you look at the set of points at which the gradient of f is orthogonal to the subspace Ax containing the top n minus d eigenvectors of the Hessian at a point, and prove that this subset is a manifold with a controlled reach. And this reach is tau, this tau is related to rho in some way. And then secondly, these top n minus d eigenvectors allow you to define a disk bundle. So you take the span of these eigenvectors at these points, and you get a disk bundle whose fiber is a disk of radius c in Ax. So this disk bundle injectively embeds in Rn, and the image contains a tubular neighborhood of m of radius some c prime. And second, and also you have control over the k minus 2 derivatives of this normal bundle. And this is sort of the key result that locally allows you to define these disk bundles, and it makes it all work. With that, I'll just conclude. So we have an algorithm for testing the manifold hypothesis and improved sample complexity bounds for k-means. And future directions include, making practical and test on real data, develop non-parametric versions for manifold fitting. So here we had a fixed tau, but it would be good to have tau adapt to data in some way. And then a better optimization over sections of a vector bundle. Perhaps we wouldn't just want to use a partition of unity, but somehow have these sections local sections talk to each other so that you maybe lose less of a factor. And then then understand the role of topology perhaps in the optimization question involved. Thank you.
Any questions? What were the sample of stream of samples? And maybe first we should have what is the visual independence of visual from some probability given I and demand before you apply your so is there a way to do it? Is it standard format?
So this is part of sort of the model of the data usually. It's the model of the data, yeah. It's the IID string. Yeah. But it can be, it's useful even like in the way we use. So if you have lots of data and you're interested in fitting up to additive error, you can just subsample, and then you can fit to the subsample. Yeah. So it comes from partly from I think Sauer-Shalach use of Sauer-Shalach, and partly from the use of Johnson-Lindenstrass. So I think there's one log there, one log in Sauer-Shalach, because the bound you get on the number of partitions is s to the VC dimension. So when you take log, you get a log s, and then the two logs get squared later in the sample complexity.